Okay, this hopefully helpful video will help to explain the quantum numbers for electrons as they exist in atoms, and their relationship to electron configurations, and maybe a couple of the interesting and creative problems you might see regarding the quantum numbers. So what I'm going to do is I'm going to explore the entire third electron energy level for an atom and work out from the quantum numbers which orbitals and sublevels and electrons exist within the third electron energy level. This type of sort of practical exercise is the best way for me to understand this type of material, so hopefully it'll help you a lot as well. So when I see that it says the third energy level, in quantum speak, that's simply saying n equals 3. So if you see n equals 3, it's saying the principal or primary quantum number is 3, and that represents the energy level of the electrons. So the energy level has been specified for us, and you can have pretty much any energy level you'd like. The first, the second, the third, the fourth, the fifth, etc. There's an infinite number of energy levels. We start numbering them with the first one, and we end with infinity, essentially. So the third energy level just picks out a particular energy level, n equals 3, within the atom. Now this energy level, like most, has a variety of sublevels. So the primary quantum number n tells us the energy level. But then we go to the quantum number L, and L is going to tell us the energy sublevels that are available. And if you've studied and you know your sort of algebraic limitations and description of each quantum number, the secondary or azimuthal quantum number, or angular momentum quantum number, gives us the energy sublevels, and it can range from 0 up to n minus 1. So if n equals 3, n minus 1 equals 2. So the math here is not difficult at all. Remembering the limits and which limits correspond to which quantum number is a bit challenging. But if you know that L ranges from 0 to n minus 1, and you know n is 3, you know that L ranges from 0 to 2. So we fill in all the counting numbers between the lowest value of L and the highest value of L, and then we have one L value for each sublevel. So L equals 0, L equals 1, and L equals 2 are our three sublevels within the third energy level. And you'll see the pattern that the fifth energy level will have 5 sublevels, etc. And that's a direct consequence of what the upper limit is and how it changes with each energy level. But now we've identified that within the third energy level there are 3 sublevels. L equals 0 is also known as the S sublevel. So you could say that we have the 3s sublevel. L equals 1 means the P sublevel. So we have the 3p sublevel. And then L equals 2 is the D sublevel. And this is, again, definitions. So there's no real understanding as to why L equals 0 means the same thing as S. It just does. And there's a historical evolution of why they used the letters S, P, and D, but that history is not necessary to understand. If somebody says L equals 2 to you, you should think D sublevel. So simple definitional stuff. So we have 3 sublevels within the third energy level, the 3s, the 3p, and the 3d, and each one of the sublevels has a particular L value associated with it. And so then we want to ask ourselves, within each sublevel, how many orbitals do we have? And that's where we look at the m, or m sub L, numbers for each energy sublevel. So I'm going to organize this out like this, where each row is going to be the set of m sub L numbers for each sublevel. And if you know the range of m sub L, it goes from minus L up to plus L. So each one of these ranges has a different origin. With n we start at 1. With L we start at 0. With m sub L we start at minus L. So if L equals 2, right, the third sublevel here, we start at minus 2, and we just count upwards until we get to plus 2. So again, not really difficult math. You might struggle to understand why we're doing this math, but that comes from an understanding of the exponents in the solutions to the Schrödinger equation, which we really don't need to know. They've sort of simplified the solutions to the Schrödinger equation to the quantum numbers, and that's why if you didn't solve the Schrödinger equation and organize the solutions, then you might have difficulty understanding why this crazy minus L to plus L limitations for M sub L. But again, you don't have to understand it to work with it. If we know that L equals 2 is the 3D sublevel, and we start at minus 2 and go to plus 2, we find out there are 1, 2, 3, 4, 5 values of M sub L for the 3D sublevel, and that means there are 5 orbitals. So a lot of times I like to put little columns here for each sublevel. We want to know how many orbitals and then how many electrons. Right? How many orbitals and how many electrons. And so for the 3D sublevel, we have 5 orbitals, and since each orbital can hold 2 electrons, one with upspin and one with downspin, then 5 orbitals would hold 10 electrons, and that's why you'll see people write 3D10 in filled sublevel electron configurations, because the 10 electrons can fit in the 3D sublevel. For the P sublevel, L equals 1, we go from minus 1 to plus 1, so we have 3 values of M sub L. So we have 3 orbitals within the P sublevels, and that gives us room for 6 electrons. So 3p6. And now hopefully you can see the relationship between the quantum numbers, which you might be less familiar with, and the electron configurations, which you may be more familiar with. Okay, and then the S sublevel, L is 0, so we go from minus 0 to plus 0, just 0. We only have 1 orbital and room for 2 electrons, and that's why each sublevel, each S sublevel, has room for just 2 electrons. So if we add up everything in the 3 sublevels for the third electron energy level, we find out there's 18 electrons sitting in 9 orbitals. 5 of the orbitals are in the 3D sublevel, 3 of the orbitals are in the 3p sublevel, and 1 orbital in the 3s sublevel. So that's the entire third electron energy level as analyzed per quantum numbers. Now, if you're going to ask some interesting questions, like how many electrons in an atom can have n equals 4, right? Again, we're going to do a very quick analysis similar to what I just wrote out in its completeness, but if you have the 4th energy level, right, you're going to want to know which sublevels exist. So you're going to count from L equals 0 up to L equals n minus 1. If n is 4, L is 3. So we have L is 0, 1, 2, or 3, and for the L values, each number has a letter designation, S, P, D, or F. And if you expanded this out, you'd find there's 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. So we could have 4s2, 4p6, 4d10, or 4f14. And if we added up all the electrons for the entire 4th energy level, we get 24 plus 6 is 30, 32 electrons. So the entire 4th energy level would have 32 electrons. And it's also helpful for me to think in terms of graphical terms. So if I'm looking at the n equals 2 energy level, right, I know there's the 2s and the 2p sublevels. I can put 2 electrons in the 2s And I could put 6 in the 2p, so for n equals 2, there's room for 8 electrons. And some of I mentioned that there's sometimes some very interesting questions that people can ask, like if n equals 2, m equals 0, and s equals 1/2, how many electrons within an atom have this description? Right? So the second energy level in its entirety would be 8 electrons. But not all those electrons have m equals 0. So we have to sort of single out which electrons in there have m equals 0. And we also want to single out how many electrons have s equals 1/2. So s equals 1/2 we should see visually as an up arrow. Right? So things are paired up spin or down spin, plus 1/2 or minus 1/2. S equals 1/2 means the up arrow electrons. So within the n equals 2 energy level, we have 8 total electrons, but only half of them have the up spin. So if I'm looking at which ones might meet that criterion, with just n equals 2 and s equals 1/2, we have 8 electrons in n equals 2, only half of them are up spin. So if we said how many electrons with n equals 2 and s equals 1/2, we'd have 4 electrons. Right? So n equals 2, the entire energy level has 8 electrons. Half of them are up spin, so we have 4 electrons. Now you figure out how many have m equals 0. Well, if you have s sublevel, m is 0. If you have the p sublevel, which is L equals 1, then the m designations for each orbital are -1, 0, or +1. And that's something that's really important that I tried to go over here, is that each m sub L value corresponds to a different orbital. So in a p sublevel, the 3 m sub L values are -1, 0, and +1, and each one of the 3 orbitals gets one of those labels. We don't know which one is which unless you put it in a magnetic field, but we know that the 3 orbitals in the 2p sublevel have designations. M is -1, m sub L is 0, and m sub L is +1, and so 2 of the p electrons have m equals 0. 2 of the s electrons have m equals 0. So now if you look at these criterion here, n is 2, the entire energy level has 8 electrons, only half of them are m equals 0. So 4 electrons would have n equals 2 and m equals 0, but then only half of those would be up spin. So if we put all 3 of these criterion on there, we would have only 2 electrons. So the entire energy level, n equals 2, 8 electrons. The entire energy level, n equals 4, 32 electrons. If you put more criterion on there, you cut down on the number of electrons that meet those criterion. Like if I said I wanted to know how many chemistry professors there were in the world, it'd be a large number, you know, a couple 100,000, maybe a million, I don't know. If you wanted to know how many chemistry professors were also bass players, that'd be a smaller number. And then if you said how many are chemistry professors that are bass players and male, you'd cut it down again by, you know, a significant factor. So looking at these criterion, hopefully you can see how I'm labeling each electron with its quantum numbers and how the electron configurations match with the quantum numbers. So this is a video that I went through quite a bit pretty quickly. If you go through it once or twice carefully and try to reproduce the examples I did or do something a little different, hopefully it'll really enhance your understanding of the quantum numbers and their relationships to the electron configurations.